So to start things off, let's go over the project. So hopefully some of you have been looking through it. This should not be coming as a surprise because we had 2 lectures on it last week when I was out at AICHE. So the main thing here is we'll be calculating, by we I mean you guys, we'll all be calculating Kirkwood-Buff integrals. So how we do that is we want to look up isothermal vapor-liquid equilibrium data. So that's a PXY diagram because the activity coefficients in the excess Gibbs are not going to be as sensitive to pressure as they are to temperature. So that's how we can get an accurate fit of the excess Gibbs. If you do TXY data, then you'd be substantially changing your activity coefficients basically. So the objective is that you are going to be locating PXY data. Now if you can get data sets that have it as a function of different temperature, that'll be an extra potential 10% credit on the project. So there's 2 sources of extra credit. One, finding data that is temperature dependent, meaning they've done multiple PXY diagrams, but not finding the data is not the sort of the end goal. The end goal is doing the extra analysis, because once you have temperature dependent excess Gibbs information, you can get access to the excess enthalpy and the excess entropy of the mixture as well. So what you're going to need to be able to do is first, by next Tuesday, so the Tuesday before Thanksgiving, is you'll have to select your paper, upload it, and also let me know. So I'll update the home page on Canvas so you can all see which papers have been submitted and which ones you can't do. So it'll be a running list for all time that I'll have of which data we've organized and tabulated. So from the PXY data, you'll then be calculating the excess Gibbs and excess volume of mixing. So not only do you need to find the PXY data, you also need to find the density of the mixtures as well. Calculate the excess volume of mixing, and to fit those calculations with a Redlich-Kister polynomial so that you can then numerically differentiate it to continue on in your analysis. So then if you do find temperature-dependent results and you want the extra credit, that means you'll also have to calculate the excess enthalpy and entropy. Then the next step would be to calculate the Kirkwood-Buff integrals, and if you do it as a function of temperature, again, calculate the Kirkwood-Buff integrals as a function of temperature. However, if we're doing this with code, it should be sort of just write a for loop or something like that, right? It shouldn't be that much more difficult. It's just a little bit more organization is required. Then, based on what we know about the mixture, is it a polar, non-polar mixture, 2 non-polar compounds, 2 polar compounds, why do the Kirkwood-Buff integrals have the form that they do? Do the molecules like each other? Do they not like each other? Is one happier in the other versus the other one? And so on. And so then your objective then is going to be analyzing your Kirkwood-Buff data, your PXY, your volume of mixing, and in your own words, draw a connection between the micro properties of the system, meaning what does the molecule look like, what is its polarity, what's its size, what's its shape, and the macro properties, which is going to be the PXY data, the volume of mixing, the excess Gibbs, and so on. So the quality of your analysis is going to be dependent on the grade. Right? So I need you to make a convincing argument that you understand both the micro and macro thermodynamics of the system. So if you can find, let's say for example, a molecular simulation, right, that also looks at these types of mixtures, then that's another way that you could strengthen your argument. Right? So there really is no ceiling to that component of it. Then the last part is to format your information. I don't have the template put together quite yet, but basically format it all in a standard approach such that this could be archived, and this is all part of a NSF grant. So you are the teaching component of the research and teaching integration that's required by NSF grants. That sounds good. And this guy's one of the ones working on that grant. So, timeline. So reporting again, so your report is going to be no longer than 4 pages. You need to include all of your data sources, your quality fits, Kirkwood-Buffs, and everything. That and any details of calculation all needs to be included in the appendices. If it's sloppy analysis, how am I supposed to know that you've done an accurate job of calculating the Kirkwood-Buff integrals? So if that's the case, then I'm not going to trust the results. So I need you to provide all your detailed analysis and code as an appendix. And then grade breakdown, basically 10% of the grade is just choosing the paper by next week. And then it's about 1/3 of the points are going to be in terms of how clearly are you presenting your calculations in your code? I mean, do you have comments in your code, all that kind of stuff? Formatting the results in terms of the template is a third of the grade, meaning that I want it to be, it's very important that I don't have to go back and reformat all your calculations. So that's a trivial thing. No one should ever miss any points on that. If you do, you're being foolish. And then a third is on the report write-up itself. So the only thing I need to provide is the template for you to grind away on this project. If you go to Canvas under the files, Mahmoud created or uploaded into the subfolder for the project a detailed book chapter of how to calculate the Kirkwood-Buff integrals, so you don't only have to rely necessarily on the lectures from last week. Any questions on the project? Okay. Back to StatMech. Okay. What we are working on is interacting systems. Now, in order to accomplish how to include interactions into our formulation of the canonical partition function, we defined this function called the configuration integral. And based on the formulation of it, the pressure of the system is directly related to the configuration integral. If we assume only pairwise additivity, meaning that if we have a collection of molecules, that we don't have to consider the energy of the system as one holistic type calculation. Instead, we'll say we're going to add up all of the individual pairs of interactions. Now, if we do that, we can write the configuration integral Okay. So again, breaking down the configuration integral, what we're doing is we have one integral over the entire volume for every particle. So what this integral is saying is that we are adding up all of the positions of all of the molecules for every configuration. So every possible location of every single molecule. Then within each of those individual contributions, we're adding up, or in this case multiplying here just based on exponential properties, we're adding up a Boltzmann factor scaled of the energy of interaction between all of them. And this gets us into the form of the canonical partition function. So this equation here is just about impossible to calculate for any real system. So instead we approximate it. And again, my service to the approximation is going to be somewhat pathetic. Basically, what I'm going to say is there's mathematical tricks that we can use to rewrite this section here. I'm not going to go over those tricks. But basically, we can take this integral and we can break it down into sort of like, almost like a Taylor series expansion type approach. Not exactly, but along the same methods. So if we assume that all of our molecules interact with binary pairs of interactions, and if we approximate this integral using somewhat of another mathematical approximation, we can show that the configuration integral is approximately equal to this function here. But keep in mind that this is an approximation of an approximation of an approximation effectively. So this is a hand-wavy way to evaluate this extremely complicated integral here. Now this 4 pi r squared contribution, that happens when we're transitioning into spherical coordinate systems. So, assuming that this approximation is appropriate, we can calculate the pressure of the system. P is equal to kBt times by the natural log of the configuration integral with respect to volume. So if we substitute it in, all right, what is the derivative, partial derivative of v to the n with respect to v?
Respect to v?
Or sorry, the natural log of this. So let's rewrite this here. So that this is equal to the natural log of z is equal to n ln of v plus n squared. Okay. So what's this first contribution here? What's the derivative of this?
N over v.
N over v. And this one here?
Minus 1 minus n squared beta over 2v squared.
Okay. So we can rewrite this in a slightly different form. Taking a lot of space on the board today. We will put the n, make it instead of an extensive volume, make it an intensive volume. So basically we have k b t over b, and then we have 1 minus beta 1 over 2b squared. And
It'd just be v because you pulled one out.
oh, right, correct. So then what we'll do instead is we'll rewrite this. We'll define a new function such that the pressure is equal to kV. And does this function look familiar to anyone? Make sure I didn't do any math wrong. This is the virial equation of state. So the virial equation of state can be derived from stat mech principles by defining the configuration integral, assuming only pairwise additivity, and then approximating that integral to a more simplified functional form. So this is okay for moderate pressure. But anything that starts to get close to, let's say, a supercritical, like the critical point, or gets close to condensation, the virial equation of state will fall flat. But the good news with the virial equation of state is that now we can calculate the second virial coefficient based on the intermolecular potential. So I'll rewrite that here, just based on doing a little quick substitution. And I switched these two here so that I got rid of the negative sign. So this allows us to relate between microscopic interactions to macroscopic measurements of pressure. So if we do have a PV isotherm, we can fit it with the virial equation of state and see approximately at moderate pressures which intermolecular potentials seem to fit which fluids at certain parameters. So we're going to do that now. So let's start off with a hard sphere. So for the hard sphere, if you recall, this goes off to infinity. So this is U, this is R. I'm going to drop the IJ just because I'll think of it as just R. So how we write the hard sphere potential piecewise function. And piecewise functions are fantastic for evaluating integrals. And that's sort of why the square well and the hard sphere are the two simplest functions that we use to sort of play around with in StatMech, because with their piecewise, then we can break them apart really trivially. So let's calculate the second virial coefficient for a hard sphere material. So we're going to have 2 pi multiplied from the integral from 0 to sigma, right, piecewise function, 1 minus e to the negative infinity, which goes to 0, plus the integral from sigma to infinity, 1 minus e to the 0. This whole thing goes to 0. So when we substitute in our hard sphere radius into this integral here, the outcome is that the second virial coefficient is equal to 2 pi sigma cubed over 3. So this means, are hard sphere fluids attractive or repulsive? They are only repulsive. Because if we substitute the virial coefficient into our expansion, we are only adding to the pressure, meaning the fluid is pushing on the walls of the container harder than it would necessarily otherwise try to. All right. Now for the next one is going to be the square well potential. We'll substitute it in as well. So for the square well, u as a function of r, we have, this goes off to infinity at the radius of the particle. We have some square well at negative epsilon energy, and then it goes back to 0 at some parameter r square well multiplied by sigma. So how far apart are these range of interactions? In a piecewise function, we write this as infinity for r less than or equal to sigma, negative epsilon for sigma to r square well sigma, and 0 for your radius greater than your final parameter, square well sigma. Okay. So in lieu of actually going out through the math, this is quite a bit more complicated to evaluate. The second virial coefficient looks like this. Okay. Not terribly complicated, but a little more complicated of a function. So what this looks like, I will define some reduced temperature, and I'll define some reduced virial equation here. And so basically I'm just normalizing this relative to what a hard sphere would have, and then this is just a relative temperature based on the attraction or repulsion interactions, kind of like a dimensionless approach to looking at transport phenomena. So if we look at this, what this function ends up looking like, so if we plot T star, and we look at this scale virial coefficient, it ends up looking something like this. And this is 0 here. So, and this would be approximately reduced temperature equals to 1. The square well fluid, as we may expect, should be attractive, right? Because we have this potential energy well where the fluid molecules want to be near one another. But that attraction only occurs when the temperature of the fluid normalized by the Boltzmann constant, is approximately the same energy as the depth of this well. So one way to think about energy transitions of molecular systems is you always want to think about what is the energy relative to the thermal fluctuations of the fluid. So, the Boltzmann constant. Who here feels confident to tell me what information is contained within the Boltzmann constant or the ideal gas constant? Who wants to volunteer? Think about it as the units, Brendan.
Oh, I was thinking about it as if you multiply the Boltzmann constant by Avogadro's number, you get the gas constant.
Yep.
So
they're the same principle, but one's just for a mole's worth of particles and one is for a single particle. What is the physical underpinnings of the gas constant or Boltzmann's law, or Boltzmann's constant?
So they share the same units as entropy?
They
They
do, but let's look at the units really a little bit more closely.
Joule per mole Kelvin for the universal gas.
They do share the units of entropy. My gut reaction is to say that is coincidental, but of course with thermodynamics everything's probably connected. So KB is equal to 1.38 times 10 to the minus 23 joules per Kelvin. So when I multiply KBT, that gives me joules. What? Now you may want to overthink this question, but what does the Boltzmann constant tell us?
is
It's a,
that, sorry,
Go ahead.
is that like the thermal energy of a single particle as it like,
yes, it is the proportionality constant between temperature and the kinetic energy of a gas. Right? So it's a constant basically saying how we relate temperature to the kinetic energy. Now, one of the reasons why Boltzmann in his theory wasn't believed, and maybe if it was believed they said who cares, it's just a mathematical approximation, is because it's very, 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 very small, right? 10 to the minus 23 joules, right, is what he calculated was the sort of the best approach to sort of understand his kinetic theory of gases and the principles of stat mech. So they had already known what the gas constant was, and so Boltzmann's connection was basically saying yes, but if we consider a fluid to be made up of small particles, which is basically the foundations of his atomic theory, this is how small molecules would have to be. Right? So they had some estimates of what Avogadro's numbers were. They knew what the gas constants were because they had done PV measurements of bulk phase fluids for quite some time. But the challenge there was that this is a very, 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 very small number, right? Inconceivably small, right? The energy of a single molecule zipping around with its kinetic energy. I'm getting hit by billions and billions and billions and billions and billions of those every square centimeter every second, and I'm unfazed by it, right? Not a lot of, doesn't pack a lot of punch. But one way to then think about how molecules behave when you think about it in terms of intermolecular potentials. If you have two particles that want to stick together, maybe it's a chemical reaction, maybe it's like a lock and key type polymer configuration, maybe it's a protein binding to some sort of biological molecule. The way to always think about it is with respect to the magnitude of the energy of interaction relative to the energy of the thermal motions of the fluid itself. So you can kind of think about this kinetically, that if I have another molecule here, I can fall down into this potential energy well. And that's a lower energy state of the system. That's a preferable configuration. However, you're surrounded by a sea of other particles. And if another one zips in and hits you, you can get knocked out quite easily. Now, the probability of getting knocked out of a potential energy well like that is going to be proportional to how deep that well is relative to the thermal fluctuations of the fluid. So if you're ever curious about length scales, time scales, and energy scales, the starting point is always what is the kBT thermal fluctuation energy of the system? Now, I should have double checked my notes on this, but I think it's on the order of, oh geez. Michael, do you remember what it is for room temperature? We can calculate it basically, right? It's just R times by T, right? So 8.314 times by 300. So let's just say this is 2400, so 2.4 kilojoules per mole. So any macroscopic process that's less than 2.4 kilojoules per mole is probably very unlikely to be in existence for a room temperature pressure system. So relative order of magnitude, how much energy do you think is stored in a covalent bond? More or less than 2.4 kilojoules per mole?
More.
Have to be more. Otherwise, molecules will be falling apart at room temperature just from two gas particles hitting into one another and causing that to break apart the entire structure. So if you have a fluid, right? Let's say we have a fluid, right, that has a square well potential here. You can get a rough estimate of whether or not you'd expect it to be in the condensed phase as a solid or liquid, or as in the gas phase, based on the depth of the potential energy well here. So even without tremendous knowledge of the details of all this stat mech mumbo jumbo, you can get a really surprisingly good estimate of the physics of a process just by looking at the thermal fluctuation energy and also considering how deep this potential energy well needs to be. So if I were to ask you, right, if I wanted to model the condensation temperature of water, for example, you could sort of in the back of the envelope know at what temperature liquid water condenses, and you could probably get a surprisingly reasonable, within an order of magnitude estimate, how deep this potential energy well needs to be of the square well potential fluid. Just based on these really back of the envelope approaches. Okay, is that sort of clear? But this is one of the tricks that professors like to use to understand sort of what things make sense and which things don't make sense. Now, we get to do what I consider one of my favorite examples in the whole class. I've got a few of them. This one's one of my faves. It has to do, because it ties everything that we've done in the whole class together into one conceptual thought experiment. It's called the Joule-Thomson coefficient. The Joule-Thomson coefficient is defined at how the temperature changes with respect to changes in pressure at constant enthalpy. Which cycle relies on the Joule-Thomson coefficient? Refrigeration. So quick question, is an ideal gas a good refrigerant? Why?
This doesn't undergo phase changes in the ideal form.
That's true. We don't actually have to rely on phase changes for the refrigeration cycle necessarily. I think the phase change I don't think we need to rely on it, but the phase change stores away a lot more energy, I think. But I think we can still do refrigeration without phase changes, just not as good. Okay, the reason for that, the Joule-Thomson coefficient is 0, basically, for an ideal gas. So alpha is the, what is alpha? Yeah, it's the coefficient, no, it's not, it's, yeah, thermal expansion coefficient, yeah. I have my note, I didn't write down this title. So alpha for an ideal gas is equal to 1 over T. Therefore, the Joule-Thomson coefficient for an ideal gas is equal to 0. Its temperature doesn't change when you change its pressure isenthalpically. And this makes sense, right? The enthalpy of an ideal gas is only dependent on the temperature. So if we were to look at a Joule-Thomson expansion valve, which is a critical component of a refrigeration cycle, we're entering in at some T1, P1, we're leaving at some T2, P2. Now what we're going to say, if we do the energy balance on the whole process, du dt is equal to 0. We're going to treat this as a steady state process. We have the summation of the mass and the enthalpy flowing in and out, plus Q plus W. And we can also, let's be thorough here. Minus P d V. V dt. Okay, so we can be really thorough with our analysis. I'm going to say this is going to be adiabatic. Q goes to 0. I'm going to say there's no shaft work done, it's just a dumb valve. I'm going to say the walls are rigid, there's no expansion. And the conclusion that we reach is that the enthalpy change has to be equal to 0. Now, going back to sort of the classical approach when we looked at energy balances, the reason why we can say heat and work are approximately 0. Now, this valve here, if you went out to your refrigeration unit at your house, it would, of course, not be room temperature. It would be cold, right? It would be cooling down. But the notion here is that we're looking at a packet of fluid as it travels through the system. So if you have a high mass velocity going through this valve, yes, you're losing some energy overall, but if you looked at per packet of fluid, that packet is losing very little energy. Now, if we integrate this into the refrigeration cycle, we have our Joule-Thomson coefficient expansion. Let's look at this right here. We have the condenser. It goes into, let's see, I'm getting this backwards here. Condenser to Joule-Thomson. The evaporator, and then goes into a compressor. Now, when it gets evaporated, we're sucking heat. This is Q cold. The condenser is outside of your house. That's Q hot. So you compress it to a liquid, you condense it, you expand it again, you evaporate it as it boils inside of your house, it cools things down. That's the standard refrigeration cycle, just as a throwback. Okay. Now, let's say I have a 612 Leonard-Jones fluid. That means that my intermolecular potential will look something like this. There will be some potential energy well where the fluid molecules will want to be near one another. As you go further away, the potential energy gets less and less. It gets more positive, actually. So this is actually the lowest energy equilibrium state of the system. Now, my question to you is I have 2 points, A to A prime, or B to B prime. So we can imagine this, right? Imagine that we have a box with a particular density, certain number of particles over a certain volume. We can then use this information to estimate, assuming that all the molecules fit into a nice periodic array, what is the average separation distance between those particles, right? This is not exactly how the fluid behaves, right? The fluid has statistical fluctuations. But in essence, based on some density, we can calculate the average separation distance. And then we can relate that to a pair potential. Now, when I say a 612 Leonard-Jones fluid, what I mean is that it's just going to be a spherically symmetric monatomic system. Now, this doesn't mean that the system has to be like that. It just means that we're approximating it as that. So, for example, imagine water with hydrogen and two hydrogens and oxygen as a single sphere. Let's just say that. My question to you, so don't blurt it out. I want everyone to think about this. If I'm running a refrigeration cycle, do I want to expand in my Joule-Thomson coefficient from A to A prime or from B to B prime? So I want everyone to think about it, rationalize it, and then we'll discuss it in a moment. See, it ties everything together. Everything's tied together nice and neatly. We get equations of state, we get cycles, we get statistical mechanics, we get intermolecular potentials. Everything's tied together in this question. That's why my favorite one of the year. I think I've said that before, but this is one of the favorite ones. Who feels they know the answer? Does anyone want to talk it through? Okay, so who's leaning, just by a straw poll, who's leaning towards A to A prime? Who's leaning towards B to B prime? So we have 1 vote for A to A, 2 votes from B to B prime, and 1 vote from A to A prime. And so, okay, so.
I feel like there are arguments to both.
Yep.
Okay.
Yeah, that's.
All right, Wilshire, what's your vote?
I probably vote B prime.
Okay, on? Rui?
A.
Okay, so pretty even split.
Yeah.
So what we're looking at here is, let's say we approximate, let's just say for hypotheticals, delta H is about delta U, just because the PV doesn't contribute too much, right? For conceptually, this thing can throw us off. So, in this circumstance here, in a Joule-Thomson valve, for a refrigeration cycle, right, that's the limiting here, right? Knowing that this is for a refrigeration cycle. We want this system to cool down, right? So U, the internal energy of a system at some higher temperature is greater than the internal energy at some cold temperature. This is basically pretty obvious conclusions. If this isn't true, it violates the second law of thermodynamics. So, when we look at this system here, when we go from A to A prime, so U of A prime is greater or smaller than U of A. Smaller here. So let's see. So U of A prime is less. I think it's just, yeah, this way here, right? And then U of B prime is greater than U of B. So,
You do want to expand from A to A prime.
no, we want to switch from B to B prime.
Yeah.
B to B prime is the right one. Because, so what's happening from A to A prime is that you have potential energy, you have energy stored in your system in the intermolecular configuration of the particles. As you expand your system from a really compressed state to its equilibrium configuration, you are lowering the potential energy of the system, meaning that you have an excess amount of energy. It's exactly the same principle as mixing water and sulfuric acid. When you mix water and sulfuric acid, you are destroying some of the energy that's formed in the hydrogen sulfate interactions. That takes it to a lower energy configuration. So now you have an excess amount of energy that is no longer stored in the intermolecular configuration, and it has to be stored in which form? Heat or kinetic energy. So you're transferring energy from the intermolecular configuration to the kinetic energy. Now when you expand from B to B prime, you're at a higher energy state. So you have to steal the energy from the kinetic energy in order to adopt the acceptable configuration. Yes?
And do we have to steal it from the kinetic energy because it's an isothermal process?
Yes.
Okay.
If it was adiabatic, then no. We would basically just suck. Q would be going into the system.
Okay.
So if we think about it this way here, this is an exothermic process, right? The final state is a lower energy than the initial state. Final minus initial, exothermic. And this one here, this is an endothermic process. The energy of the final state is distinct from the energy of the initial state. So, this sort of one ties everything together very nicely. And it ties sort of how to think about fluids. So now if you, with this knowledge, basically, you can now design potentially a refrigeration cycle for an arbitrary compound. You don't have to go into the lab and measure all the properties. And this is really the predictive power of statistical mechanics. Classical mechanics is all made up. Classical thermodynamics is all made up, basically. We've got a formulation. We need to know certain properties, but there's no way to actively predict those properties. So thermo, in a classical sense, is a formulation that allows us to aggregate experimental data and use that information to calculate more advanced processes, right? So only measuring a PV isotherm for a gas and its heat capacity, we can now estimate how it should phase transition in a mixture. Right, so that's pretty cool, right? But at the end of the day, we can't predict that PV isotherm. We have to measure it and then correlate it with the cubic equation of state. We can't predict heat capacities necessarily. With stat mech, we can predict those, right? We can predict with appropriate models molecular rotations, bond vibrations, the kinetic energy, intermolecular forces, and all of that. So that's the real strength of statistical mechanics, is that all the weaknesses of classical thermodynamics kind of fall apart when you actually try and do predictive things. Like classical thermo just aggregates that information, but here we can actually begin to predict how fluids should behave based on simple rules of how we think molecules should be attractive and repelled from one another. And this is nice because it ties in basically energy balances, processes, intermolecular forces. So it's a really nice example. What we're going to be talking about on Friday, there's a couple of options, but we're either going to be talking about dense fluids or phase transitions from a stat mech perspective. I haven't decided which one we'll do yet. But soon we'll be covering radial distribution functions, these squiggly lines that everyone can see. This is basically the next step in density. The virial equation of state, what we talked about today, that's okay for moderate densities. But once we start talking about real liquids become astronomically more complicated than even non-ideal gases. Non-ideal gases are relatively straightforward. But dense fluids like water or any other liquid, those are extremely difficult. So we're actually ending a little bit early today. It's a bit challenging to introduce the radial distribution function in 5 minutes. Anyway, well, see you all on Friday. Please take a look at the project. Let me know if you have any questions. Yeah, have a good rest of the week.